Welcome to today's lecture on one of the most fascinating and counterintuitive phenomena in innovation science, the copy-to-transform paradox. Let me start with a question that has puzzled researchers for decades. Why do some scientific fields that encourage intensive copying and adherence to established methods eventually produce more radical breakthroughs than fields that constantly chase originality? At first glance, this observation seems completely backward. We're told from childhood to be original, to think outside the box, to avoid copying. Yet when we look at the history of major scientific revolutions, we see a paradoxical pattern. The most transformative innovations often emerge from communities that first invested heavily in mastering and copying existing frameworks. Today we'll explore this paradox in depth. We'll examine cumulative culture, high-fidelity transmission, knowledge structures, and the cognitive mechanisms that make copying a prerequisite for transformation. Let me define the paradox more precisely. Consider two hypothetical research communities. Community A emphasizes mastering standard methods and copying classical solutions. Community B encourages everyone to pursue unique approaches and original ideas from day one. Our intuition strongly suggests that Community B should produce more innovation. After all, they're constantly trying new things. But empirical reality shows something different. Community A, despite its apparent conformity, often produces the bigger, more transformative breakthroughs over time. So why does this happen? The answer lies in understanding cumulative culture and how knowledge actually builds over time. Let me give you an analogy. Think about language and poetry. You cannot write revolutionary poetry without first mastering the language. First, you copy grammar, syntax, and vocabulary. You master the standard forms. Only then can you bend and break rules in meaningful ways to create genuinely new poetic forms. Imagine someone who refuses to learn English and instead tries to immediately invent their own random words. They won't create beautiful poetry. They'll create meaningless gibberish. This is the essence of the copy-to-transform paradox. Copying is not the opposite of creativity. It is often the necessary foundation for it. Now let's dive deeper into the concept of cumulative culture. This is a term from cultural evolution theory. Cumulative culture refers to the ability of a population to accumulate modifications and improvements over multiple generations, building knowledge that no single individual could discover alone. Humans are uniquely capable of cumulative culture at scale. This is arguably our species' defining feature more than language or tool use. Each generation starts with what the previous generation knew, adds a little more, and passes it on. Knowledge accumulates like compound interest. But here's the critical point. Cumulative culture only works if transmission fidelity is high. If each generation garbles the message, knowledge doesn't accumulate, it degrades. Think about the children's game called telephone or Chinese whispers. A message is whispered from person to person. With low-fidelity transmission, the message degrades rapidly. By the 10th person, the message is unrecognizable. But if each person carefully copies exactly what they heard, the message can travel through dozens of people intact. Scientific communities are like this. They need high-fidelity transmission of core methods and theories. This is why we have textbooks, standardized curricula, problem sets, and apprenticeship-style lab training. These are technologies for high-fidelity cultural transmission. Let me introduce a visual model that helps explain the paradox, the knowledge tree structure. Let's plot innovation rate over time for both communities. Time is on the x-axis, innovation rate on the y-axis. Community B shows constant but modest innovation from the start. They're always trying new things, so they get a steady trickle of small novelties. Community A shows a different pattern. Initially, innovation is near zero. This is the copying phase, where everyone is mastering the core. But then, boom! Innovation explodes. The explosion happens when enough people have mastered the core so deeply that they can see its limitations and possibilities. Now they can transform it. Let me give you a historical example. Consider mathematics in ancient Greece. Early Greek mathematicians spent generations copying and mastering methods from Egypt and Babylon. They were not being particularly original at first, but then around 300 BCE, Euclid synthesized all this copied knowledge into the elements, creating an entirely new axiomatic framework that transformed mathematics forever. The copying phase wasn't wasted time. It was necessary preparation. Without deep mastery of existing methods, Euclid couldn't have seen how to reorganize and transcend them. Now let's talk about cognitive mechanisms. Why does mastering a core free up capacity for innovation? Human working memory is severely limited. Classic research by George Miller suggested we can hold about 7 chunks of information, though more recent work suggests the number is closer to 4. Every problem you try to solve consumes some of your limited cognitive resources. If you're simultaneously trying to figure out basic methods and pursue novel ideas, you're splitting your attention. In Community B, cognitive load is high. You're spending mental bandwidth on basic methods and trying to innovate. The resources left for genuine innovation are tiny. In Community A, methods are automated through practice. They run on autopilot. This frees up massive cognitive resources for genuine innovation. Think about learning to drive a car. At first, every action requires conscious thought. As a novice, you're thinking about the gas pedal, the brake, the steering, the mirrors, all at the same time. You cannot hold a complex conversation while driving. But once you're an expert, driving becomes automatic. You can now hold deep conversations, plan your day, or think about complex problems while driving safely. The same principle applies to scientific methods. Master them until they're automatic, and you free up mental bandwidth for genuine creative thinking. Let me show you a temporal pattern that emerges from the copy to transform dynamic. I call this the innovation wave pattern. Let's plot innovation rate over time for both communities. Time is on the x-axis, innovation rate on the y-axis. Community B shows constant but modest innovation from the start. They're always trying new things, so they get a steady trickle of small novelties. Community A shows a different pattern. Initially, innovation is near zero. This is the copying phase, where everyone is mastering the core. But then, boom! Innovation explodes. The explosion happens when enough people have mastered the core so deeply that they can see its limitations and possibilities. Now they can transform it. Let me give you a historical example. Consider mathematics in ancient Greece. Early Greek mathematicians spent generations copying and mastering methods from Egypt and Babylon. They were not being particularly original at first. Then in 300 BCE, Euclid synthesized all this copied knowledge into the elements, creating an entirely new axiomatic framework that transformed mathematics forever. The copying phase wasn't wasted time. It was necessary preparation. Without deep mastery of existing methods, Euclid couldn't have seen how to reorganize and transcend them. Now let's try to quantify this paradox with some back-of-the-envelope calculations. These are illustrative models, not precise predictions. Let's assume each scientist has 100 units of cognitive capacity per year. Let's define some variables. C is capacity devoted to learning core methods. I is capacity devoted to innovation attempts. M is mastery level, ranging from 0 to 1. P is the probability that an innovation attempt succeeds. Here's the key assumption. The probability of innovation success depends heavily on mastery level. Let's model it as P equals M squared. This captures the idea that innovation requires deep mastery. Community B splits capacity evenly from the start. C equals 50. I equals 50 every year. After 1 year, mastery reaches 0.5. They've learned half the core material. So P equals 0.5 squared, which is 0.25. Each innovation attempt has only a 25% success rate. They make 50 innovation attempts with 25% success, yielding 12.5 innovations. Community A takes a different approach. For the first 2 years, C equals 100, I equals 0. They focus entirely on mastery. After 2 years, mastery reaches 1.0. They fully mastered the core. Now P equals 1.0 squared, which is 1.0. Their innovation attempts succeed 100% of the time, because they understand the field so deeply. In years 3 and 4, they shift full capacity to innovation. C equals 0, I equals 100. Each year, they produce 100 times 1.0, which equals 100 innovations per year. Let's compare total innovations over 4 years. Community B produces 12.5 innovations per year for 4 years, totaling 50 innovations. Community A produces 0, 0, then 100, then 100, totaling 200 innovations. That's 4 times as many. Now this model is obviously oversimplified. Real mastery is never 100%, and innovation probability isn't perfectly quadratic. But it captures the key insight. Delaying innovation to build mastery can yield dramatically higher total innovation. Let's look at some real-world examples from the history of science that illustrate this paradox. Consider the development of quantum mechanics in the early 20th century. The physicists who created quantum mechanics, people like Heisenberg, Schrödinger, and Dirac, spent years mastering classical mechanics, electromagnetism, and thermodynamics. They drilled the standard problems relentlessly. They learned to manipulate Hamiltonians, Lagrangians, and wave equations in their sleep. But this deep mastery is precisely what allowed them to see where classical physics broke down and to envision something radically new. Between 1925 and 1930, they transformed physics completely, introducing matrix mechanics, wave mechanics, and the uncertainty principle. Without years of mastering classical physics, this transformation would have been impossible. You cannot transcend what you do not understand. Let's jump to a modern example, the deep learning revolution in artificial intelligence. From the 1980s through the 2000s, neural network researchers mostly worked with standard architectures, multi-layer perceptrons, backpropagation, convolutional nets, lots of copying. Then in 2012, AlexNet achieved a dramatic breakthrough in image recognition. This launched the deep learning revolution. But notice, the breakthrough built on decades of mastered fundamentals. The researchers knew backpropagation inside and out. This mastery let them see how to scale it up with GPUs and massive datasets. Then came transformers, GPT models, diffusion models, and more. Each innovation built on deeply mastered prior work. Now let's ask a critical question. When does this paradox break down? Are there situations where premature novelty seeking is better? The first condition is when the field is fundamentally broken. If the core is wrong, not just incomplete but actually wrong, then copying it is harmful. Think about pre-Copernican astronomy. The geocentric model was fundamentally wrong. Mastering Ptolemaic epicycles didn't help you discover heliocentrism. It might have hindered you. The second condition is diminishing returns. If a field reaches a point where additional mastery yields almost no new insights, then it's time to explore. The third condition is when copying culture becomes pathological, when it suppresses all deviation and questioning. Then you need rebels. There's a crucial difference between healthy copying, which preserves a core while allowing questions, and pathological copying, which enforces dogma and punishes deviation. The copy-to-transform paradox works best in healthy, growing fields where the core is mostly correct and still being actively refined. What are the implications for how we train scientists? This has practical consequences. First implication, we should not rush students to produce novel research before they've mastered fundamentals. There's a problem in modern PhD programs. Students feel pressure to publish novel findings within 3 to 4 years. This often happens before they've truly mastered their field. The result is often incremental work, small tweaks and variations, not transformative breakthroughs. An alternative model would allow a longer mastery phase, perhaps 5 to 6 years, followed by a period of explosive productivity when the foundations are solid. Second implication, we should value replication and teaching as legitimate scholarly activities, not just novel research. Replicating classic experiments is how you master methods. Teaching forces you to understand material deeply. These are not wastes of time. They're investments in future innovation capacity. Let me return to the language analogy with more depth. The key insight is that copying creates a shared vocabulary. When everyone in the community has mastered the same core methods, they share a vocabulary. Researcher A can communicate complex ideas to researcher B very efficiently. This shared vocabulary enables rapid collaboration. You don't have to explain basic concepts. You can jump straight to the cutting edge. More importantly, innovations can build on each other quickly. When everyone understands the foundations, new ideas propagate rapidly through the community. In contrast, when everyone pursues unique approaches from the start, they lack a shared vocabulary. Communication becomes difficult. Innovations remain isolated. There's a concept from evolutionary anthropology called the ratchet effect. Let me explain how it relates to our paradox. A ratchet is a mechanical device that allows motion in one direction, but prevents backward motion. A cultural ratchet means knowledge accumulates and doesn't regress. Each generation starts at least where the previous one ended. High-fidelity copying creates this ratchet effect. If transmission is faithful, knowledge doesn't degrade between generations. Each generation builds on the previous one. The ratchet prevents slipping backward. This is cumulative culture in action. But without faithful copying, the ratchet breaks. Each generation has to rediscover basic knowledge, and progress stalls. Is there empirical evidence for the copy to transform paradox? Let me share some research findings. Research on patent citation networks shows that the most impactful patents tend to come from inventors who first spent years working in established technological trajectories. They mastered existing technology deeply before introducing transformative innovations. Studies of scientific breakthroughs show that breakthrough authors typically spent 5 to 10 years mastering their field before producing their breakthrough work. Research on apprenticeship in art and music shows similar patterns. Great innovators like Picasso or Stravinsky spent years copying masters before developing revolutionary styles. Laboratory studies using experimental microsocieties show that groups with high-fidelity social learning accumulate more complex cultural knowledge over generations. The evidence is remarkably consistent across domains. Copying is not the enemy of innovation. It is often the foundation. Different cultures and historical periods have struck different balances between copying and innovation. Let's explore some variations. East Asian education systems traditionally emphasize extensive mastery of fundamentals before encouraging deviation. Students spend years drilling basic problems. Western education systems, especially in recent decades, tend to emphasize creativity and original thinking earlier in the educational process. So which approach produces more innovation long-term? The evidence is actually complex and depends on the field. In highly cumulative fields like mathematics and physics, the mastery-first approach seems to have advantages. You need that solid foundation. In less cumulative fields, or fields where the core is less well established, earlier experimentation may be beneficial. So how do we resolve the copy-to-transform paradox? Is it really a paradox, or just a misunderstanding? The paradox only seems paradoxical if you assume that copying and innovation are opposites, that they're in conflict. The resolution is to recognize that they're not opposites. They're sequential phases in a single process of creative development. Copying comes first, building mastery and shared foundations. Then comes transformation, generating genuine novelty that builds on that solid foundation. Copying is not the opposite of creativity. It's the ladder that lifts you to heights where genuine creativity becomes possible. Think about athletes. They drill fundamentals endlessly, copying perfect form from coaches. Only then can they improvise and create signature moves. Let me conclude with some practical implications and recommendations for scientists, educators, and institutions. For individual scientists, don't be ashamed of the copying phase. Embrace it. Replicate classic experiments. Work through textbook problems. Master the canonical methods. This is not wasted time. It's foundation building that will enable breakthroughs later. For mentors, don't rush students to produce novel findings too early. Allow time for deep mastery. For institutions, value replication studies and teaching excellence, not just novel publications. For funding agencies, support longer-term projects that build capacity, not just quick novel results. Let me summarize the key insights from today's lecture on the copy-to-transform paradox. First, copying is not the opposite of innovation. Intensive copying of core methods builds the foundation necessary for genuine transformation. Second, cumulative culture, which is humanity's superpower, requires high-fidelity transmission of knowledge across generations. Third, mastery automates basic operations, freeing up cognitive resources for genuine creative thinking at the edges of knowledge. Fourth, When a community shares a common foundation through copying, they develop a shared vocabulary that enables rapid, collaborative progress. Fifth, the paradox resolves when we recognize that copying and innovation are not opposing forces, but sequential phases in creative development. Here's a final thought. Stable cores of knowledge don't constrain creativity, they enable it. A strong foundation lets you build higher and explore farther. The most radical innovations in science, art, and technology almost always come from individuals who first achieved deep mastery of existing knowledge. Thank you for your attention. I hope this lecture has given you a new perspective on the relationship between imitation and innovation, between copying and creativity, and between tradition and transformation.